So here we go. So how does this integral look different than stuff you've seen before? So far, integrals you've seen have had what in both, either no bounds at all or definite bounds, as in two numbers, as in finite numbers, right? One of them wasn't infinity. And so the question is, how might you deal with this, and what would this represent? So does it make sense that if you kind of had no idea what to do, you could plug in a really big number for infinity, like 1,000, 10,000, et cetera, and you could keep plugging in bigger and bigger and bigger and bigger numbers for that upper bound and kind of look at what happened as that upper bound got bigger and bigger and bigger? So how does that get rephrased into sorry, my infinity looks like an 8. How does that get rephrased? This idea that you're making that upper bound bigger and bigger and bigger and bigger as a limit, yeah. So you're going to change that upper bound into a variable. And the letter that's commonly used is B. You can choose any letter you want, but B is for Beth, so that's a really good letter. And to make these two things be the same, you have to say that B is getting bigger and bigger and bigger. So to do that, you put a limit as B goes to infinity. One over x squared dx. So do you agree that that's the same thing? Mm-hmm. Okay. And you cannot drop the limit sign until you've taken the limit. So even though that's like, 6 characters of writing, you cannot be lazy and leave it off on your written homework. We will take off points, okay? It will happen. On your web assign, I can't tell what your work is doing, so you can do whatever you want. But if you're going to show me something like a quiz or a test, you have to write the limit thing again, because you haven't actually done that operation yet. So now, how about the integral? Can you find that definite integral now? Yeah, so let's rewrite that as x to the negative 2. What's the antiderivative of x to the negative 2? Negative x to the negative 1, or negative 1 over x. That's evaluated from 1 to b. So you got the limit as b goes to infinity, negative 1 over b plus 1 over 1. So what is that going to equal? As b goes to infinity, negative 1 over b goes to 0. So this is going to go to 1. And what we say then is that the original integral, which I'm just going to call integral now, the integral converges to 1. So the questions will be phrased as, does this integral converge or diverge? Tell me which one. If it converges, what number does it converge to? Yes?
Remember, usually when you have a limit and integrals following it, you're supposed to cancel out. Why in this way?
No, you're thinking of a derivative and an integral. If you have a derivative and an integral and it's sort of set up a special way, then they cancel out, but limits and integrals do not cancel out. You're misremembering something. That's definitely not always true. And then one last thing, what would this represent? So integrals mean areas under curves, right? So this means we're looking at the curve 1 over x squared. We're looking at the positive quadrant only, so don't worry about the negative quadrants. What is one nice point this thing goes through? 1, 1, yep. So 1, 1. And then as the x's get larger, it decreases to the x-axis, right? Okay. So what we effectively said is that the area under this curve from 1 until infinity is equal to 1. And that's because the curve sort of decreases quickly enough. Does the idea make sense?
Yeah.
Okay.
So it's like a cake. You cut it in half, you stick the half piece on top of that, you take the second piece, cut that in half, take one piece, stick it on top, and just keep doing that over and over and over, and it goes up to infinity.
Yeah. So that's actually a little bit different, because that's adding sort of like, that's not decreasing continuously, it's decreasing in a very specific way. That's something called a series. We're going to do that in chapter 11.
All right.
Okay, but it's kind of like that. That's like, you kind of have the right idea. Yep. Okay. So this next thing that you have on your notes just tells you how to properly translate those infinities into limits, which is pretty much related, like almost like just what we just did, right? If you have an upper bound that's infinite, you just take the limit as that upper bound goes to infinity. So that makes it, replace it with a letter to have it go to infinity. If you have an integral from negative infinity to some number, the negative infinity has to be sort of taken care of. Does that idea make sense? So you replace that negative infinity with some letter, and you can use whatever you want. And you take that lower bound to negative infinity. And if you have an integral that has infinite bounds on both ends, then you break it into two pieces. And this number c that you choose can be whatever you want. A really common thing to choose is 0, because 0 is nice and easy to plug into most functions. Yes?
So why aren't there limits on C?
Because I kind of figured that once you get to C, you realize that you can use the first one and the second one to do the rest of it.
Okay.
Does that idea make sense?
Yeah.
That's your first step, and then you go back to the previous two steps to do both of those. And if at this stage either one of these things diverges, the whole thing diverges, there's no need to check the second one. Okay, so let's do a few examples. So the integral from 0 to infinity e to the negative 2x dx. So first thing, write it as a limit. Limit b goes to infinity, and what changes in your integral?
Per bound.
Upper bound, yep. 0 to b e to the negative 2x dx. Now, this is the kind of antiderivative that you should be able to do without having to actually do the substitution. Does that make sense? If you do make the substitution, you have to change your bounds, including the one that's got b in it, okay? So just keep that in mind. So what's the antiderivative of e to the negative 2x? Great. Evaluated from 0 to b. Okay, then input b, we have negative 1/2 e to the negative 2b plus 1/2 e to the 0. And technically, what's a better way to write that first term? Because, you know, it's kind of, I think if I believe that this thing was going to 0 more if I wrote it as a ratio, as in one ratio.
It's 1 over e to the 2b.
That's great. It's 1 over e to the 2b. Don't miss that negative sign, but yeah. So 2, so the e to the 2b just joins the other 2 into the denominator, right? What's e to the 0? 1. Okay, great. And now can you look and tell me what's happening to that first term as b gets very, very large? Goes to 0, yep, so this is 1/2. And so your final answer is, does this integral converge or diverge? It converges to 1/2. I promise we will have an example of divergence as well. In these cases, that's pretty much always going to be that this limit is infinite at the end. That means your integral diverges, as it doesn't go to a finite number. Okay. Oh no! Negative infinity and positive infinity. But, this is 1 over x squared plus 1 is a special kind of function. Do you remember what kind of special function it is?
Tangent.
It does integrate to arctan. I was referring to its evenness as it kind of makes it special. Remember that? Yeah. So why are even functions special? What can you do with symmetric integrals and even functions? Yeah, you can do twice the integral from 0 to infinity. And that's nicer, right?
I was here yesterday.
Just later, okay? All right. So now change your infinity to, change that integral into a limit. So twice the limit, b goes to infinity, integral 0 to b, 1 over x squared plus 1. Okay. So what's the antiderivative of 1 over x squared plus 1?
Is that arctan?
Arctan. So we have twice the limit b goes to infinity, arctan of b minus arctan of 0. Sorry, habit of writing theta whenever, 0. Okay. And I suspect many of you might be crying. You're like, oh my gosh, I don't know what happens to arctan when b goes to infinity. Anybody remember? So what does how do you get arctan's graph from tangent's graph?
Flip it.
You flip it in a specific way. Okay, so tangent has asymptotes at just like one period of it has asymptotes where? Negative pi over 2 and it looks like this like S-shaped thingamajig, right? When you find the inverse, you flip the x's and the y's, and that reflects over the diagonal, as in y equals x. So all of the vertical asymptotes now become horizontal asymptotes, yes? Okay, so you have a horizontal asymptotes at pi halves, you have another one at negative pi halves. And arctan looks like that, right? Okay, so what happens as your value inside arctan gets big? Where does arctan go? Pi over 2. So this is 2 times pi over 2. Or pi. So our integral converges, diverges, converges to pi. But to evaluate that, you have to sort of know what arctan looks like. And officially, that actually is pre-calculus. You are supposed to know what arctan looks like. Okay? Like, you can't forget all the previous math you had before this class. Yes?
So if you're taking the integral from negative infinity to infinity of arc, and you're looking at arctan, that's an odd function. So so when you go in the negative direction, you have a...
You're thinking of the wrong thing, okay? We're not anti-differentiating arctan. We're anti-differentiating 1 over x squared plus 1.
Oh.
We're looking for the area under 1 over x squared plus 1, which looks something like that approximately. Okay, like as in the specifics of where those inflection points and things are is different, but it looks about like that. If we were actually integrating arctan from negative infinity to infinity, I'm pretty sure that diverges, but I'd have to work it out to be certain. But
Like
the graph that we're looking at, yeah, let me get back to that one, okay? Because I can't like, it's not on the notes, and I would like to just save it for later, but okay, so later. But that wasn't the thing we were actually looking at the area under the curve for. Does that make sense?
Yeah.
Okay, great. All right. So the next one. So 1 over x. So we had the very, very first example was the integral from 1 to infinity of 1 over x squared, right? And that converged, yes? And it converged to 1. And 1 over x looks a lot like 1 over x squared, right? So if I were to graph them at the same time, let me graph 1 over x squared. They both go through the point 1, 1, right? Okay, so there's 1, 1. 2, if this is y equals 1 over x, the next point is 1, 1/2, right? What if I graphed, in a different color, what if I graph 1 over x squared? So after, that also goes through the point 1, 1, right? Is it above or below the graph of 1 over x at 2? Below, because it'd be 1 over 4 there, right? Okay, and then here the graph would be above. You can confirm that by plugging in some numbers. Okay, so your suspicion is that, well, maybe this is going to converge because that function does like decrease to 0, and maybe it gets small enough that it actually adds up to a number, but it's actually going to diverge. Crazy, huh? So let's see. 1 to infinity, 1 over x dx. That's equal to first the limit as b goes to infinity, 1 to b, 1 over x dx. Okay, what's the antiderivative of 1 over x? Don't forget those absolute value bars. Although in this case, we do only have positive, x's, so it's probably not as important. So you have the limit as b goes to infinity of natural log of b minus natural log of 1. What does the natural log function look like? What's one point it goes through? 1, 0, yep. And it looks like this, right? As in, there is the y-axis is a vertical asymptote. Thou shalt not log negative numbers or 0. Yes. Commandment number 3. And it does increase rather slowly, but this function is increasing. So what happens as b goes to infinity of ln b? It goes to infinity. And natural log of 1 is 0, so we have infinity. So this integral does what? It diverges. Yeah.
Yeah, just to recap, and I know we probably went over this, the diverge is like when it gets really big, and the converse is when it goes to a number.
Yes, but diverging also could be that it goes to negative infinity. So diverging means it just doesn't go to one specific finite number. Because you can also diverge by oscillating, but that doesn't really come up very much with these kinds of examples. Corey, do you have a question?
If there was a constant with infinity, can you just run infinity?
Yes.
For example, if it was infinity minus 1.
Yes, you could. Yeah.
You want us to put the integral divergence for like negative infinity or infinity?
We'll just check your answer. Does that make sense? Like, we'll look at your work, and if you have said infinity and then concluded that it diverges, we'll just check that you have the right thing. So just show your work neatly so that we can actually read it. Okay. So far, all of the problems we've seen have been pretty simple antiderivatives. It's totally game for some of these things to involve stuff that we've learned in this chapter. Does that make sense? As in, like, integration by parts. Yes? Okay? So just keep that in mind. So integration by parts, big hint that you're going to use it is that you have a multiplication of product. Exactly. So first, let's make this a limit. What's my b going to go to this time? Negative infinity. Very good. Integral from b to 0, x e to the x dx. Okay, so put your integration by parts work sort of like on the side. So what's your u going to be? What's your dv going to be? U is x, spectacular. Du is dx. dv is e to the x dx, and v is equal to e to the x. Okay, so we have the limit. B goes to minus infinity. Don't forget parentheses because this integral will expand into two pieces and the limit applies to both of them. So in integration by parts, uv minus integral v du, right? Integral u dv, that's the formula? Yeah? Okay. So uv is x e to the x minus the integral from b to 0 e to the x dx. I made a slight mistake on purpose. What am I missing? Yeah, I need the bounds. That first term no longer is being integrated. It's like done, right? And since we have a definite integral, we have to evaluate that from 0 to b, yes? So don't forget that. Okay. So limit b goes to minus infinity. So let's do two things. I'll just color code this so you can see it better. So for this thing, first we plug in 0, which gives us 0. Minus, then we plug in b, right? Which gives us b e to the b. Yes? Okay, great. We have minus e to the x, because the antiderivative e to the x is e to the x, from b to 0. Or 0 to b, sorry. Said that backwards. Is everyone okay with what happened there? You have to be quite careful with the second term because you're going to have a distribution of a negative, okay? Just be very, very careful. So limit b goes to infinity, negative infinity, sorry. Negative b e to the b minus parenthesis e to the 0, which is 1, minus e to the b. Close your parentheses off. And let's just distribute the negative and then talk about how to proceed with that whole negative infinity business. Minus 1 plus e to the b. Oofda. Is everyone okay? Yes.
I'm gonna wait for what you're about to ask.
Yeah, maybe you should. Okay, so b is going to negative infinity, which means b is getting very, 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 very large and negative, right? Like I think about those, personally I think of those as two separate components. I can make b negative and then make it get very large. Does that idea make sense? So what I typically do with limits at negative infinity is I say this is the same thing as the limit as b goes to infinity. That takes care of the whole getting large business, right? But I can't forget about the whole negative stuff, right? So I change every single b into a negative b. So that becomes negative b, e to the negative b, negative 1 plus e to the negative b. Do you agree that that does the same thing? Yeah, it definitely does, doesn't it? You could officially also do it by like replacing b with a different letter. You could say like let c equal negative b or something like that. That would do the same thing. I'm just being a little bit lazy.
But you don't have to do that, right?
No, you don't have to do that. I mean, like this is a true statement, right? These two things are equal. They do the same thing, so it's fine.
But what does that simplify? Like, why would you take that extra step?
Well, let me do the rest of it, and I think I'll explain why in that process. Does that make sense?
Yeah.
Okay. So this becomes b over e to the b. I don't know why I just wrote x. Sorry, habit. B over e to the b minus 1 plus 1 over e to the b. Okay. So what you can do next is you can evaluate every single term in the limit individually. Does that idea make sense? So we're going to find the limit as b goes to infinity of this first thing. What happens as b goes to infinity with negative 1? It just stays negative 1. What about 1 over e to the b? Where does that go? 0. Now this first limit is something that you were supposed to have learned in Calculus 1, but depending on the curricula that you had, maybe they didn't teach it to you. Have you heard of this thing called L'Hopital's rule? L'Hopital's rule? I call it the hospital rule.
Did we go over it when the class started?
In the class that I taught you last summer, yes, I did go over it. It was in section 4.4 of your textbook in case you need to reference it, but that's where it is. It lets you deal with limits of the form infinity over infinity or 0 over 0, as in both things go to infinity or both things go to 0. And it kind of is the quotient rule that you wished was. It's not actually the quotient rule, okay, like the quotient is something different, but it says that the limit of this expression is the same as the limit of the ratio of their derivatives. So this limit is the same thing as the limit of 1 over e to the b. And that minus 1 is like totally separate. It's sort of like just hanging off on the end. That's what L'Hopital's rule says. And it only works if your limit is infinity over infinity or 0 over 0. If your limit's not of that form, you can't use it. And some people like you to put like a little h over your equal sign to tell me that you've used L'Hopital's rule. And some people also make you say it's infinity over infinity just to check that you know. But in my opinion, that's more Calc 1. If you can just do the rule correctly, great. I mean, as long as you made a true statement, I'm okay with it, okay?
As long as we get the right answer, you know that we used the rule correctly.
He says, and you've showed me some work, right?
Yeah.
Okay, does that make sense? So this limit goes to -1. Okay, so somebody asked the question about why did I even bother with the whole negative infinity change thing, right? So one reason is that because you're plugging negative numbers in for this b, but you're actually getting our ratios because e to the negative power makes a ratio. And I just don't see any easier way to notice that I'm going to use L'Hopital's rule unless I've done that. Does that make sense? So I've always found in Calc 1, I don't think the book does it this way, I think I just made it up on my own because the book confused me, that I just think it's easier to deal with positive infinities, and this is how you can make it happen. So, yeah.
I don't, like, the way I would have done this is just like 4 or 5 steps ago, I would have just plugged it in right away, because I mean.
But you can't just plug in infinity and say something is true.
But, yeah, so like, you don't even need L'Hopital's rule for this, because you can just
Yeah,
see
you do.
something increasing, but the bottom's increasing quicker, you can just kind of.
Yeah, but L'Hopital's rule is the thing that proves that.
Okay.
Does that make sense? Like, I know if you're in the computer science, you probably use something called big O, which has to deal with certain functions getting bigger faster than other functions.
Yeah.
So, but in this class, you can't use those tricks. You've got to show me like the why that thing works.
Okay.
Does that make sense?
Yeah, that makes sense.
Yeah, so that's the reason you have to use L'Hopital's rule.
Okay, cool.
So if it, like in my stats class where we're doing stuff like this, actually, she's not making us like do this step formula because like we're past this. We kind of know that if we have an exponential on the bottom, it's always going to go to 0 if you have a polynomial on the top. Like, but at this stage in your mathematical development, you have to show me that you know that rule. Does that make sense? Okay. Alrighty. So what does this integral do? Sorry, it converges to -1.
Great answer. Do we have to write convergence too?
It depends on what the question states, right? So like for WebAssign, it's just, you know, actually they might even have a box you check converges or diverges, and then they have a place for you to put in the, I can't remember, but they might be putting the number too. I can't remember. Okay? Let's read the directions, okay? But I think it pretty much, if you say it's an answer, I'll understand that you know it. If you give me a number, I'll think you know it converges to that number. Okay, so we had 2 integrals that looked a lot like this. Do you agree? We had the integral from 1 to infinity of 1 over x squared. That was the very first thing. That did what? Converged. And then we had the integral from 1 to infinity of 1 over x, and that diverged. And so the question is what number for that p is sort of like the changing point? You change from converge to diverge. Yeah?
Alright, so is that like an even odd thing, or is that gonna be some different?
That's what this is going to explain. Okay? So like this will explain. So we have a few cases. So when you anti-differentiate 1 over x to a power, you can do that as long as the power on your x, you can use the reverse power rule as long as that power is not 1, right? When the power is 1, it's a bit special because the antiderivative of 1 over x is natural log, right? So we're going to handle this in 3 cases. So my first case, so case number 1, is that p is equal to 1. That gives us the integral from 1 to infinity, 1 over x dx. You know what this thing did. What does this thing do? This thing diverges. So see example, I think it's example number 3, right? Yes, it is. Okay. Okay. So case number 2 that we're going to kind of break into later cases, we're just going to assume that p is not equal to 1. So anything but that. So then find the integral from 1 to infinity, 1 over x to the p dx. That's the limit. Lots of letters, sorry guys. B goes to infinity, 1 to b, 1. Can I make that x to the negative p instead? Is that okay? All right, great. Okay. So what's the antiderivative of x to the negative p?
X to the negative p plus 1
X to the negative p plus 1, great.
times
divided by negative p plus 1.
Is that 1 minus p, or is that negative p plus 1
It is the same thing as 1 minus p, which I'm going to rewrite it that way in just a second.
Okay.
Yeah.
For the purpose of this exercise, are we assuming p does not equal 0?
If p equals 0, you have 1 over x to the 0, which is 1. That's not a problem.
Well, I mean, but that wouldn't really be any math, that'd just be, oh, look, you have 1. That's,
Just
The rule still works.
the rule still works. My point is the rule still works for that. It doesn't matter if x is 0. The rule still works. So now first we're going to plug in b, right? We get, I'm just going to change it to 1 minus p. b to the 1 minus p over 1 minus p minus 1 to the 1 minus p power over 1 minus p. Yes? So is there a constant there that I can factor out of my limit? The 1 minus p, that's in the denominator, so that's going to be a 1 over 1 minus p. Limit b goes to infinity. B to the 1 minus p minus, and 1 to any power is just 1, right? Except 0 power, but we assumed that p was not 1, so that's not a problem. Wait, what am I saying? 0 power, yeah, 1 of the 0 is still 1. I don't know what I'm talking about. Okay. So everyone okay with all the work that I did there? Okay. Now the part that's going to determine convergence or divergence is this bit right there, right? If that thing goes to 0, we're going to have convergence, right? If that thing goes to infinity, we're going to have divergence, yes? You buy? Okay. So here's the first thing we're going to look at. If your p is bigger than 1, then do you buy that 0 is bigger than 1 minus p? Do you agree with that? I.e., 1 minus p is a positive or negative number? Is negative. So you have something raised to a negative power in that case. Does that idea make sense? So that means that that piece is going to go to 0. Is that okay? Yeah, okay. So in this case, the integral converges. And the reason is because the limit as b goes to infinity, b to the 1 minus p is going to be equal to 0. And that's because that exponent is negative. What about if p is less than 1? Then 0 is less than 1 minus p, i.e. 1 minus p is positive, right? Does that idea make sense? So you have something that's going to infinity being raised to a positive power. What's going to happen then? This is going to diverge. So it converges if p is in the interval from 1 to infinity. Diverges if p is in negative infinity to 1 inclusive.
So why is divergence exclamatory, whereas convergence isn't?
Say that again?
Why is divergence exclamatory, whereas
What is it? Oh, because of the whole x equals 1 case from the very top.
yes, but you put an exclamation mark on divergence?
Say that again?
Divergence has an exclamation mark. Just because it's there.
Oh, that's just because I was being cute.
Okay.
Yeah, no other reason. So tell me, without any work, what would the integral from 1 to infinity of 1 over x cubed dx do? It'd converge. Does that make sense? Because that power is bigger than 1, yes? As in the p. What about the integral from 1 to infinity of 1 over root x? It's x to the 1/2. That's going to diverge. The idea is that this is actually above the whole 1 over x function, so it's a bigger number than the 1 over x function when you go to infinity. So that's why that's a way to tell that they converge or diverge quickly. But the kicker is it only applies to integrals of the form number to infinity. The fact that the first number can be something other than 1 as well. Well, 1 isn't actually very important because if it diverges from 1 to infinity, it diverges from 2 to infinity as well. So it's the thing that happens at the end that matters, not so much the beginning. Okay. So those are all of the kind of a general introduction to the ones where you have infinite bounds. Another case that we have are things where you have infinite discontinuities. And I think that this is best explained with an example. An infinite discontinuity is a vertical asymptote. Okay? So back in Calc 1, these questions were asked in a way to evaluate the integral, and they said, like, if it exists, and you were told that the only way that you could find these areas under curves is that you had to have a function that was continuous on the interval that you were given, right? Is this function continuous on the interval that you are given? No. Where's the problem? 0. So you have to change 0 into like a variable of some sorts and take a limit as your function approaches said variable. So once again, we'll use b. Limit b goes to infinity. Oops, what am I saying? Not infinity. Sorry, we're gonna fill in where it's going in a second. B goes to someplace. TBA. Integral b to 8, that's x to the negative 1/3 dx. And I am going to be a little bit picky about how you write your work for these things. You have to do this part right. When you come at 0, are you coming at 0 from this side or from this side?
Positive side.
The positive side, because you're inside the interval 0 to 8, right? So that should say 0 plus. And I'll be checking that you do two things. You get the right number, and you get the right plus or minus. Does that make sense? If 8 were the problem, it'd be going at 8 from the left or 8 minus. Okay? And other than that, it proceeds, the rest of it's pretty much the same. What's the antiderivative of x to the negative 1/3? 3/2 x to the 2/3, yep, which I always do the power first. That's just my personal, because I can't like keep track of what I'm doing. B to 8. That's the limit as b goes to 0 plus 3/2 times 8 to the 2/3 minus 3/2 times b to the 2/3. Okay. So what really matters is what's happening with this b part. Can you plug 0 into 0 to the 2/3? Is that okay? Yeah, you just get 0, right? So that's fine. So you're going to have whatever 3/2 times 8 to the 2/3 is, and this is algebra 2, okay? How do you evaluate 8 to the 2/3? Cube root 8 squared. You can also do it in the opposite order, but it's far easier to root first than square first. So the cube root of 8 is 2. 2 cubed is 2 squared is 4, yep. So that's 3/2 times 4, or 6. So this integral converges to 6. These integrals will diverge typically if you still have a 0 in the denominator. Like as in when you've done your interdifferentiation, you still get 0 in the denominator, that's kind of when divergence is going to happen. That's a good rule of thumb. When you have a 0 in the denominator, like as in if your antiderivative had been x to the negative 2/3, for example, and you would have had 3 over 2x to the 2/3, then plugging in 0 would have been an issue and the integral would diverge. Does that make sense? Yeah. So zeros in the denominators are what are causing problems for these kinds of things. Is everyone okay with that? All right. Okay, this one, who's the problem? 2. Stinking 2. So limit b goes to someplace, b to 5. I'm going to write that as x minus 2 to the negative half. Okay, so how is b going to 2? From the left or from the right? From the right. Okay, can you anti-differentiate x minus 2 to the negative 1/2 without having to use a substitution? I think so, right? So you're going to get x minus 2 to the positive half, right? What's its coefficient? 2, right? 2 over 1. Evaluated from b to 5. So we have 2 root 5 minus 2 root b minus 2. Technically, the fact that, so what happens, the first term just goes to 2 root 3, right? That's easy enough. Where does the last term go? 0. And technically, the real reason you can also say it goes to 0 is because b goes to 2 plus, you're plugging in numbers that are a little bit bigger than 2. Does that make sense? Like 2.01, 2.000000001. And you do that number minus 2 and you get a positive thing, right? So the thing you're square rooting is positive. Like had it been b goes to 2 minus, you probably made a mistake, but then you couldn't even root those numbers because they'd be a little bit negative. Okay. Awesome. Okay, your favorite one. Secant. Does secant have a problem in 0 to pi halves? You have to kind of remember what secant looks like. Oh no. Yeah, so how I was taught to graph this, I think it's a great method. Cosine looks like this, right? So secant has asymptotes wherever that thing is 0, right? And then it kind of does this sort of business. Yeah. They look a bit like parabolas, except for they're not parabolas because parabolas aren't bounded on the sides. Yeah.
I thought the graph of cosine was 0 at 0 and whatnot.
Nope, you were wrong. That's sine. Sorry. Sine is 0 at 0. Cosine is definitely 1 at 0. You just
Well, if you input x equals 0, it's the x value, right?
yes, and on the unit circle at the x value at 0, the x value is indeed 1. Yes, so I know I'm right. That time I'm right. Other times I'm not, but that time I am. Okay, so the integral from 0 to pi halves of secant x dx is limit b goes to pi halves, and from what side? This time it's the left. Integral 0 to b. All right, what's the antiderivative of secant? Natural log of secant x plus tan x from 0 to b. So we got the limit b goes to pi over 2 minus natural log value secant b plus tan b minus natural log absolute value secant 0 plus tan 0. Okay. I'm going to leave the first part alone just for a second. So secant b plus tan b. Just want to talk about that last number. What is secant of 0? 1. You should know, and what is tangent of 0? 0. So that's ln of 1. You should know that natural log of 1 is equal to 0. Okay, so like On your test, we are making like the integral questions worth more points. Like instead of 5, most of them are worth 8. And if you don't do something like say ln of 1 is 0, you probably will lose a point. Okay, just FYI. Yes.
I might have misheard you, but you said you're making the integral questions worth more.
Well, not more than something else, but more than they were in your quizzes.
Right, but
For example, in your quizzes.
all we're doing is integrals, so what type of integral? I think I just misheard what you said.
No, I was just referring to the number of points a question is worth on the quiz versus a homework problem. And the points aren't even equal because they're in different categories in your weighted grade.
Okay.
Does that make sense? It's just
Yeah.
that would allow where you might have lost a half a point on a quiz, or maybe we didn't take off anything at all because we felt like it was too harsh. There will be a point taken off if you don't say ln of 1 is 0 like on a test.
Okay.
Does that idea make sense?
Thank you very much.
Yeah, no problem. Okay. So now what happens to secant, looking at this picture, what happens to secant as b goes to pi halves from the minus? Where is secant b is going to infinity? Do you buy that? Okay, what about tangent? Tangent's picture, well, you guys knew this was impressive. So happy. What happens to tangent of b as you go to pi halves? Also goes to infinity. So the stuff inside your natural log is going to infinity. You're natural logging a big number, which goes to infinity. So this thing diverges. Okay. So the previous examples that we had both had bounds that were problems, as in left bound or right bound. The trickiest ones are when they're in the middle, because that's where actually you're probably going to get the wrong answer if you just don't observe that there's a middle point causing a problem. So who's the problem point here? 1. So break this into the integral from 0 to 1 plus the integral from 1 to 3. And you got to check them both individually. And what you really hope, because there'll be less work, that you hope the first one you check diverges, because then you're just like, oh, I'm over, it's all over, I'm done. If the first one converges, you got to check the second one as well, and then your original integral converges to the sum of those two things. Okay? So let's check the integral from 0 to 1 dx over plus x minus 1. Be careful, don't say equals, as in, don't put an equal sign here. Does that make sense?
Yeah.
Why? Because it's only half of it, right? It's not the whole thing. So,
It's less than that.
yeah, but anyway, it's part of it, not all. Just like restart. Okay. So limit b goes to 1 from what side? The left, correct. Yep. If you imagine the interval from 0 to 1, I have to draw a picture because I'm just kind of visual. You're going at 1 from that side, right? That's definitely from the left. Okay, what's the antiderivative of x minus 1? Great, from 0 to b. So limit b goes to 1 minus natural log of b minus 1 minus natural log absolute value negative 1. Ooh. This is a teensy bit tricky, but we reviewed. This is what natural log of x looks like, right? Okay. So as b goes to 1 minus, do you agree that b minus 1 goes to 0? Does that make sense? I don't know why I wrote like a minus 1 there. I should take that off, sorry. Okay. And so what happens to natural log when you plug things in that are close to 0? It goes to negative infinity. So that's negative infinity minus 0 or negative infinity. Diverges. Yep.
Oh, wait, since you're adding those two together, if the other one went to positive infinity, would it actually converge at zero?
No, it doesn't. So I know, and even, I think even if it's like the arctan thing that Devin was asking about, I don't think it converges. I think that if either one diverges, the whole thing diverges, even if they sort of, I haven't thought carefully enough about it to tell you exactly why it's wrong, but for now, just know that it is, okay? But I promise I'll come back with a better answer. I just can't think of it off the top of my head right now. Because I've had the same thought myself, and I was told in no uncertain terms that I was incorrect. Okay. And the last thing that's on your notes is something called the Harrison theorem. So sometimes you can't actually compute an integral, but it's useful to know, but you know that something kind of similar, you know about that thing's behavior, and you can use comparison to determine what happens to the integral that you care about. So suppose we have this relationship. We have a function f of x that's bigger than or equal to g of x, and they're all positive. So let's draw a picture of what's going on. Probably can fit this on the side. So you have some function f, and f is, so there's my f of x function, and some function g. And g lives past some point a. G goes crazy, but g of x is below f. And if you think about these in terms of they mean areas under curves, it should make complete sense what these statements should say. If the integral from a to infinity of f of x dx is convergent, which means the area of the purple curve is a finite number, right? Then the area of the blue curve has to also be a finite number, right? And that should make total sense. And vice versa. Would it be true that if the one above diverges, the bottom one diverges too? Other way around.
No.
If the smaller one is infinity, then the one that's above it has to be infinity too, right? And that idea is going to come up again in, here's how well I know this book, chapter 11, section 4, okay? For a different idea, a different thing, but the basic idea is the same, is that if your smaller thing diverges, so does your bigger one. This one I think is positive as well. If your bigger one converges, so does your smaller one. The positivity is necessary because of the whole negative infinity business, and you can probably make it work for negatives as well if you use absolute values in a clever way, but for now we're just going to look at positive things. Does that idea make sense? Yeah.
What about the 1 over x and 1 over x squared situation?
Well, that definitely sort of confirms that you can't. Okay, so there's, I don't know what I just drew, sorry. X-nay that. Y equals 1 over x. They intersect at 1, right? Y equals 1 over x squared, yes? Okay, so it's just not the proper relationship to determine convergence or divergence, right? 1 over x is above 1 over x squared. Does that make sense? So you can't make a conclusion comparing those two things. Does that idea make sense? And vice versa, 1 over x squared convergent doesn't mean the bigger one does, right? So, but you could compare 1 over x and 1 over root x, which would be something like that, right? You say, oh, I know 1 over x diverges, right? 1 over root x is above that from the point 1 on. Therefore, from 1 to infinity, 1 over root x diverges. But to show that something converges or diverges based on another one, the inequality has to go the right way. As in, to show convergence, you must be bigger than a converging thing. To show divergence, you must be smaller than a diverging thing, right?
Right, do you mean smaller as in like the power of it?
I mean smaller as in the y values from some point on are less than the,
Okay.
does that make sense? Okay, so let's use that to show this one thing is convergent or divergent. So can I just, because I'm going to run out of time, will you believe me that this thing converges, like just for now? Because it's not very hard to figure out.
Sure.
So this thing converges to 1. Like if you do the limit thing, you get that that equals 1. And I'm pretty sure if you want to practice, just do that on your own, okay? All right, now the next thing you look at is this is even, right? So the integral from negative infinity to infinity, e to the negative x squared dx, that's twice the integral from 0 to infinity, e to the negative x squared dx, right? And if we can show that integral from 0 to infinity of stuff converges, the rest of it will converge too. So we're going to show integral 0 to infinity, e to the negative x squared dx converges. And here's how. Break into the integral from 0 to 1, e to the negative x squared dx, plus the integral from 1 to infinity, e to the negative x squared dx. Do you agree the first part converges? As in, this thing is just a number. It's a function, it's never 0 in the interval, right? It's just an area under some curve, some number. Okay, for the second part, so note that if x is bigger than or equal to 1, so how is x squared related to x? Who's bigger? Yep. And then negative x squared is less than or equal to negative x, right? Because you divide by a negative or multiply by a negative 1, the inequality flips, yes? Okay. So then e to the negative x squared is less than or equal to e to the negative x, right? Do you buy that? Because e is an increasing function. If you plug bigger numbers into e, they keep getting, they're larger than plugging smaller numbers into e. And then since the integral from 1 to infinity e to the negative x dx converges, so does the integral from 1 to infinity e to the negative x squared dx by comparison. Fancy math word. Thus, the integral from negative infinity to infinity of this thing converges. Phew, man, right on time.